Welcome to Calculus. Today, we are diving into one of the most powerful tools in mathematics and physics linear ordinary differential equations with constant coefficients. Imagine you are driving a car over a bumpy road. The way the car bounces and settles down is governed entirely by these equations. By the end of this video, you will understand exactly how to predict the future of such systems, turning complex calculus into simple algebra. Let us get started. Now that we know what we are studying, let us break down the name itself. Why do we call it a linear ordinary differential equation with constant coefficients? Linear means an unknown function and its derivatives are never squared or multiplied together. Ordinary means things change with respect to just one variable, like time. Constant coefficients is the physical part. The mass of our car or the stiffness of its springs do not magically change while driving. They are fixed numbers. Finally, we focus on homogeneous equations, meaning there is no outside force pushing the system after it starts. It just moves on its own. Building on those definitions, let us look at how this translates into a mathematical formula. This long equation is the standard form of an nth-order linear homogeneous differential equation. The letter y represents the unknown function we want to find, like the position of our car. The variable x is our independent variable, usually time. The terms with fractions are the derivatives, telling us the velocity, acceleration, and so on. The symbols an down to a0 are our constant coefficients, representing those fixed physical properties like mass or resistance. If we increase a coefficient like mass, the system becomes more sluggish. Because it equals 0, we know it is homogeneous. This formula we just saw leads us to an important question. How do we actually solve it? We need a magical function that, when we take its derivatives, looks almost exactly like the original function. If they look alike, we can multiply them by our constant numbers, add them up, and get exactly 0. In all of calculus, there is only one function that behaves this way, the exponential function. So we make an educated guess that our solution will look like e raised to the power of m times x, where m is an unknown constant we need to find. Now that we have our educated guess, let us see what happens when we plug it into a second-order equation. We are setting out to transform our calculus problem into something much simpler. First, we take our guess. Y equals e to the power of m times x. To substitute this into our differential equation, we need its derivatives. Using the chain rule, the first derivative brings down a factor of m. Taking the derivative again for the second derivative brings down another m, giving us m squared times the exponential. We now have all the pieces we need to substitute back into our original equation. With our derivatives ready, let us perform the substitution to find our final result. We replace the second derivative, the first derivative, and the original function in our second-order equation. Notice the absolute magic of choosing the exponential function. Every single term now contains that exact same exponential piece. Because it is a common factor, we can factor it out completely to the front. Now, logically, for this product to be 0, one of the parts must be 0. Since an exponential function can never actually equal 0, the polynomial inside the parentheses must be the part that equals 0. This resulting algebraic equation is called the characteristic equation. We have successfully turned a complicated calculus problem into a simple algebra problem. So, we have proven that this substitution works for a second-order equation. This brings us to a beautiful mathematical pattern. What if our system is more complex, like a tall building swaying in an earthquake, requiring a third or fourth-order equation? The exact same logical pattern applies perfectly. Every derivative simply turns into the variable m raised to the exact power of that derivative's order. A third derivative becomes m cubed, a second derivative becomes m squared, and the original function just becomes the number 1. Because this pattern is so reliable, we can instantly write down the characteristic equation for any higher order differential equation without even doing the substitution steps. Now that we have our characteristic equation, we solve it to find its roots, which we call m. Where does this final solution formula come from? It comes directly from combining our individual exponential guesses. If the roots are real numbers and distinct from each other, we simply place each root into its own exponential function and add them together with arbitrary constants c1 and c2. These constants represent initial conditions, like starting position. If the roots are repeated, we multiply the second term by x to keep them mathematically independent. If the roots are complex numbers, Euler's formula transforms them into real-world sine and cosine waves, representing physical oscillations. Before we move on, let us see this with a concrete example. We are given a second-order differential equation where the second derivative minus 5 times the first derivative plus 6 times the original function equals 0. Our goal is to find the unknown function y. Why do we use our new method? Because it is a linear equation with constant coefficients. Our very first step is to convert this calculus problem into an algebra problem by writing down the characteristic equation. We replace the derivatives with powers of m, giving us m squared minus 5m plus 6 equals 0. We then factor this quadratic equation to find our roots. Continuing with our algebra, we set each binomial factor equal to 0. Solving these gives us our two roots for the system, positive 2 and positive 3. Because we have two real distinct roots, we use the first rule we learned for building the solution. We place each root into its own exponential function and combine them with arbitrary constants. This gives us our final general solution. Physically, because both exponents are positive, this represents a system whose response grows exponentially over time, moving further and further away from its starting point. Now that we have found our solution, let us prove that it actually works. We are setting out to perform a complete solution verification. To do this, we must substitute our answer back into the original differential equation. If it is truly correct, all the terms will cancel out and leave us with exactly 0. First, we need to find the derivatives of our proposed solution. Using the chain rule, we find the first derivative by bringing down the 2 and the 3 from the exponents. Then, we take the derivative again to find the complete second derivative. This sets us up perfectly for the final substitution step. With our derivatives calculated, we are ready for the final mathematical reasoning. We plug the original function, its first derivative, and its second derivative back into the left side of our original differential equation. We carefully expand the expression by distributing the negative 5 and the positive 6. Next, we group the similar terms together. We gather all the terms containing e to the 2x and all the terms containing e to the 3x. When we add the coefficients in each group, they both evaluate to exactly 0. The entire left side collapses to 0, perfectly matching the right side. This proves beyond any doubt that our general solution is mathematically sound. Having verified our first result, let us tackle a slightly more challenging problem. We want to solve a specific third-order differential equation. This represents a more complex physical system with multiple interacting parts, like a multi-stage electronic filter. We start the exact same way we did before, by writing the characteristic equation. This instantly transforms our third-order calculus problem into a third-degree algebraic polynomial. Looking closely at the coefficients, we can recognize a familiar pattern from algebra. This specific polynomial is actually the exact expansion of the quantity m minus 1 raised to the third power. Continuing from our factored polynomial, we can easily see the roots. We have a single real root, positive 1, but it is repeated 3 separate times. Because the root is repeated, we cannot just write 3 identical exponential terms, as they would collapse into one. To keep them mathematically independent, we multiply the second term by x and the third term by x squared. We then factor out the common exponential part to write the final answer cleanly. Physically, the presence of the x and x squared terms tells us that the system's behavior will grow much faster over time than a simple exponential function alone. Now that we have calculated these different types of roots, let us visualize what they actually mean in the real world. Look at the graph on your screen. The horizontal axis represents time, and the vertical axis represents the displacement or position of our system. The green dashed curve shows an overdamped system caused by real distinct roots, which sluggishly returns to rest. The blue solid curve is a critically damped system caused by real repeated roots, returning to rest as fast as possible without bouncing. Finally, the red dotted curve shows an underdamped system caused by complex roots, creating a bouncing, oscillating motion that slowly dies out over time. We have covered a lot of ground today, so let us reinforce the most important ideas. First, solving a linear differential equation with constant coefficients is fundamentally a process of turning calculus into algebra. By using an exponential guess, we create a characteristic equation. Second, the roots of this algebraic equation directly dictate the physical behavior of the system, whether it is sluggish, critically damped, or oscillating. Finally, these equations are the absolute backbone of engineering and physics, used to design everything from electronic circuits to earthquake-proof buildings. You now have the mathematical tools to predict the future of these complex systems. Great job!